Steinhauer here, welcome back. Continuing a discussion of the constituents of the Milky Way galaxy, the things that make it up. And you can see we've got our classic view of the visible part spectrum of the Milky Way galaxy. And you can see the disk of the galaxy and the bulge of the galaxy and these dark molecular clouds. Something else to notice is when we went through our components of the Milky Way, all of the present gas and dust and all of the present high ionization nebulas are all in the disk of the galaxy. The halo of the galaxy, which has some stuff in it, there's no ionization nebulae, these pink regions. There's none of these dark clouds. There's no blue stars in the halo of the galaxy. All of the young stars and present star forming regions are in the disk of the galaxy. So this leads to some very big differences in the components of the stars that make up the disk of the galaxy as opposed to the halo of the galaxy. Here is, you can see it in another galaxy. Not only is most of the star formation happening, well, all of the star formation is happening in the disk of the galaxy. Most of it, if you look at this Whirlpool galaxy, is confined even to the spiral arms of the galaxy. That's what these spiral arms are at some level. They're density waves. And so the density of material within these spiral arms are a little bit higher than they are elsewhere. And that's what it takes to trigger star formation. When you slam these molecular clouds together, you increase the density and you increase the chance that you'll have these clouds collapse and form stars. And you can see you've got in these spiral arms themselves, you've got these very dark molecular clouds. You've got these very bright pink regions, which are regions where stars are forming right now. And you can even see some blue stars here, which have to be those very young, very massive, very bright stars that don't live very long at all. And so you see all of those things associated with this, not only the disk of the galaxy, but along the spiral arms of the galaxy itself. So this leads to some interesting differences between halo stars and disk stars. So let me ask you if you can work this out. On average, which do you think are older, disk stars or halo stars? Go ahead and see if you can answer. Okay, let's talk about it now. Again, all of the present star formation is happening in the disk of the galaxy. So all of the young stars in the galaxy have to be in the disk. The halo has to be all old stars because there's no stars forming in them right now. So the disk of the galaxy has both young and old stars, but on average, these stars have to be younger than the halo because the halo has only old stars. So for which question, the question which on average, which stars are older, those have to be stars in the halo. Again, the halo will have only old stars. The disk will have both young and old stars in it. Okay, here's one that's a little bit more tricky. On average, which stars contain more heavy elements at their surface? What do you think, disk stars or halo stars? Okay, this is much more subtle than the first question. We know that the halo stars on average are older. And we also know that old stars in their centers have gone through lots of burning, potentially hydrogen to helium, potentially helium to carbon, and greater. But those elements are trapped in the centers of those stars, right? Just because the sun has burned through half of its hydrogen in the core doesn't mean we see that at the surface. In fact, we see at the surface pretty much the elemental abundances that the sun formed with, as do almost all stars. And so when we're talking about heavy elements, we're talking about all the heavy elements. And so you might know that the universe, when it began, was almost entirely hydrogen and helium. When we talked about supernovae, we mentioned this fact. And the only reason why we have many of those very heavy elements in the universe at all is because they've been recycled, they've been created in supernova and recycled into the galaxy. And so the first generation of stars, the oldest stars, should have no heavy elements in their surface at all. should have only hydrogen and helium. The next generation of stars should have a few of those hydrogen, non-hydrogen and helium elements. And every subsequent generation of stars should have more and more of these heavy elements in the clouds that they formed from, and still having those elements at the surfaces of those stars. And so it tends to be that the younger a star is, the more recently it was formed, the more generations of these supernovae had gone off, the more heavy elements they tend to have at their surface. And so it's disk stars that tend to be more metal rich, we say. And so those are two big differences of the components of these galaxies. The disk stars are younger on average and have more heavy elements at the surface, and the opposite, of course, for the halo stars. In fact, it's a pretty stark difference. When we look at the halo stars, you can have, we haven't seen any first generation stars, but we've seen stars that have 100 times less elements in the sun, 200 times, 1,000 times, 10,000 times less heavy elements at their surface. These must be stars that formed near the beginning of the galaxy. And on average, when you look at halo stars, 0.02 to 0.2% of them are heavy elements beyond helium. And so we can sort of develop and when you look at the disk stars, it's more like the sun, which has about 2% of heavy elements, stars of all ages. And so you can see you've got two components. The halo formed first, and then star formation stopped in the halo, and you still have this old population of stars there. The disk stars formed early there, but they've kept forming, and they're still forming today. And so you have many more subsequent generations for the chemical abundance of these heavy elements to enrich in the disk of the galaxy, and we see that in the stars today. Okay, I'll stop there, and when we come back next time, we'll talk about how the Milky Way formed and also how to measure the mass of the Milky Way. See you there.